Okay, guys, let's get started. Um, I appreciate all you guys coming here for the class. I know I've been recording this class and making it convenient for students, and many of them are not showing up to class, which it's okay to me. But you know what? Your suggestion was good. Maybe next semester when I teach this class, I'll give a bonus for attending classes. But too late for this semester. But hopefully you guys will get a better understanding of the contents that I'm teaching here. So instead, I found myself it's much more effective. I'm there actually in person, other than just watching video myself. But of course, you do get an advantage when you play the video. You can play double speed and you save you half of the time. So, well, we're going to continue. As I mentioned last time, we are. Let's see if I get the microphone, everything turned off. Yeah. So today I'm going to continue to talk about the class B and class AB amplifiers, which again the power stage. And next week we're going to spend 2 lectures on op amps, and then upon next week again, guys, don't come next week because I won't be here, so I'll be teaching online next week. Yeah, for 2 classes that will be taught online. So just if you want to join online, feel free to do that. But if you got something else you want to watch it later, it will be recorded and then posted. But I'll be spending the 2 lectures on op amps. And then once we come back on April 29th, we're going to have a quiz on this chapter. Again, do the homework. And review the lecture contents, and you'll be able to get 100% if you can do the homework correctly. Again, my goal is not to penalize. My goal is to encourage you to do what you need to do. Of course, if you don't watch the lecture, if you don't do the homework, you probably have a hard time to get the answers. That's the way it is. And then on that same day, on the 29th, Monday, I will do a thorough review of the whole semester, and we're going to recap what we have done for the semester and draw a main line to connect the dots of the whole semester. And then you'll get a better understanding of everything. And then on Wednesday that week, which is May 1st, I'm going to do a whole office hour. You guys should come and come with questions. Then hopefully we'll work together. It will be in person. Yeah. On that Wednesday. And then on Friday, of course, we have the final exam. So I decided not to give any new lectures on that week because Friday's exam, anything that I deliver on Monday and Wednesday will be too quick for you to digest and do any homework on it. So that's why I'm not giving any new contents for that week. So any questions? Okay. So on Monday, we already talk about class A amplifiers. And again, I want to emphasize, why do you need these amplifiers? Well, the goal of amplifiers is to amplify a small signal, and eventually we do something with it. Whether you're going to drive a speaker, whether you're going to drive an actuator, or whether you're going to do, well, whatever, crazy, you need power. So at the end of your amplifier, you need this power stage, which you amplify your small signal to do some action. And that power amplifier is what we're talking here. So it's still amplifier. It's still mimic the small signal amplifier, but just that its power is much bigger. When the power is much bigger, we are concerned because on the class A, what happens? Efficiency is only 25%. So think about it. If you drive something at, say, 100 milliamps, let's say 10 watts. So all you need is total 1 watt. You waste 75%, which is 0.75 watts. You probably don't care. Nobody would care. 0.75. I can deal with that. But what happens if you drive an actuator, the example I had to drive the steering wheel of your car? That's going to need about 3 kilowatts. 3 kilowatts. So if you're wasting 75%, what happens? You're wasting more than 2 kilowatts.
More than 12 kilowatts, you have two problems. One is that you're going to waste a lot of power, which is not good. Secondly, the power that you wasted is going to become heat. You have to dissipate the heat, otherwise your system will get burned. You're going to smell, right? And 2 kilowatts is a lot of power. You know, you go home, you turn on your stove, like if you have an electrical one, or if you go barbecue, if you go to camping, you have this little like electrical cooktop. That is about 2 to 3 kilowatts. How hot that can become, right? So that's why we need to look at different type of amplifiers. The stage A is perfect in the sense it gives you a perfect sine waveform. There's no distortion, there's no cutoff. You got a perfect sine waveform. The problem is only it got only 25% efficiency. You're wasting 75% of the power, which is okay for small power, like watts, maybe 1 watt, 2 watts, 3 watts, whatever. That small power is okay. But when you go to tens of watts or hundreds of watts, this system is messed up. It can't work. So how do you reduce consumption or loss and increase the efficiency is what we are talking about, class B. So let's get back a little bit. So what happened? Why is the class A amplifier wasting so much power? Well, because remember the class A amplifier is composed by a current source and a load resistance and a transistor Q1. And the current source, of course, you can join the Q2 as well. That it doesn't matter. It just emulate a current source. So what happens is that you need a constant current going this way, and you have a current IL going this way, and you have current coming IE1. So regardless of your output, that current is always conducting. The current, the bias current, is always there. Which means even if your output is 0, what happens? You still have current going through. And you have current going through, you have VCC, and you have minus VCC. So apparently, you will have a loss of S plus equal to S minus equal to I times VCC. Then you're wasting 2 times. That is wasted at 0 output. 0 output, which means your output 0. There's no power output. But your transistor is still working hard to draw that current. You're wasting all that energy. Okay, when you have output, of course, you're still drawing that current, but your output can only go up to I, right? Which is only 25% of total power that is delivered. So that's why the problem. So in order to address this problem, we propose a class B amplifier. Where's my class B? Okay. Oh, I drew it on the wrong page. Okay, that's fine. So I'll move this page afterwards. So we have class B then. So the class B amplifier is an improvement of class A. Instead of having a current source, we actually have 2 emitter followers back to back. You look at the top one. The top one, if you look at only the top one, not this. The top one is an emitter follower because the input is connected to the base and your output is at the emitter. So that's an emitter follower. But if you look at the bottom, if you don't look at the top, only look at the bottom, the input is connected at the base and our output is connected to the emitter. So it's an emitter follower. So it's a 2 emitter follower, one N-type, one P-type, that connect back to back. So it's like 2 emitter followers working together. One will be for the positive half cycle, one will be for the negative half cycle. So yeah. What is it? No, there's no more. No, that's the VCC is on top of there. Yeah, there's nothing else. So this is just 2 emitter followers connected together with output in parallel. When it's working, you will see we have positive half on the top and negative half on the bottom. Why is that? Well, See, look at it, what happens when the input is 0. Okay, so if Vi is 0, what happens? If input is 0, both transistors will be in cutoff mode. And we can analyze why. Well, because, for example, if we assume this conduct, what voltage would you get at the VO? Assume that for now, suppose Qn is conducting, you would get minus 0.7 volts, right? Yeah, because it's conducting, so it's like 0.7 volts down there. And then, okay, if this is minus 0.7, but here is this RL, so there must be a current flowing through RL. And that current going which direction? It's minus. So the current flows in this direction, right? Minus, right? Voltage minus, the current goes up. And the current goes here. See, current cannot go up because the top transistor can only conduct current in the top to bottom direction. So where would the current go? This current and this current, they will all go down, which means this transistor has to conduct. Otherwise, the current has no place to go. Now, if this transistor conducts this minus 0.7, what voltage needs to be here? This minus 0.7, this 0.7 drop between emitter and the base. So you need minus 1.4. So which means this will become minus 1.4 volt, which is not correct because initially it was 0. How come it become minus 1.4? So which means it cannot be. So which means this one should not conduct and this one will not conduct. So that's why Qn and Qp cut off. So both will be cut off if it's 0. In fact, if Vi is less than 0.5, larger than minus 0.5, it will be all cut off. In fact, between 0.5 and 0.7, there will be a little bit conduction. Above 0.7, it will fully conduct. So that's what we have for the first point. So the second point is that now if Vi is larger than 0.5, what happens? So if Vi is larger than 0.5, which means this, let's say here is let's assume it's 0.7, right? So if 0.7, this will conduct, suppose. And this will conduct, this will be 0 volts. And this 0 volts, this bottom here, this 0.7, and this 0, so you see here, it's the voltage drop is 0.7. So therefore, you have Qn on, but Qp off. So if it's positive, right? So 0.7, the top is on, and this is 0, and this is 0.7 with 7. So therefore, this will off. That is on. So the current will flow from the top down this direction. Of course, how much will be VO? Your VO will be Vi minus VBE N. So the voltage input Vi minus the voltage drop at the base to emitter, you get the voltage here. Right? So that's what you get. And of course, how much current would you get? No, this Vi is the input. Okay, so let me change this. What I meant is little is a low is a subscription Vi. So it's Vi input. And this current IL equal to IEN equal to VO over RL. So that's what we got for the load current and for the output, right? So what happens if Vi is less than 0.5, minus actually. So if it's less than minus 0.5 volts, and suppose, let's see, we got some numbers here. Let's suppose this is, say, 5 volts. I'm just giving larger than 0.5, it can be anything. Let's say 0.5. And what I'll tell you is that minus, let's say minus. So if this is minus, most likely, the top transistor will be off. Why? Because if this is minus 5, I mean, look at it. The voltage drop here has to be more than like minus 5.7. So this must be like off. Actually, that is true because this is minus 5, this will be on. If this is on, so this is minus 5, what is your here? Going to be minus 4.7 volts, right? Because this is minus 5. So the voltage drop over here is 0.7. I mean, minus 4.3. Right? So that's the voltage drop between the emitter and the base is going to be 0.7. So this is off. So QN is off. Well, why? Because if this is minus 4.3, this is minus 5, you see, this is higher than this. So the emitter current is higher than the base, so QN is off. And that's easy to understand. So QN is off, QP is on. If QP is on, QP is off, so how would the current would conduct? So the current going this way, and the current will go like this way. See, the current is minus negative. So VO is going to be VO is VI plus VBEP. That's the PMOS. So it's the input plus 0.7, whatever that voltage is going to be, you got your output. And the current right now is going to be negative. So the current IL is negative, but it's going to be VO over RL. It's the same thing. So your current VO over RL. So this means that for the positive voltage, the top is conducting, you get output. For the negative voltage, you get the bottom conducting, you get a voltage output. The only problem is that in the middle, there's no output. Output is 0. So between minus 0.5 and 0.5, the output is 0. So if we plot okay, so if we plot the relation, like I want to write the equation here. So if I is larger than 0.5, and we have VO equal to VI minus VBEN. If VI is less than 0.5, these are all volts. But larger than minus 0.5 volts, our VO is 0. If VI is less than minus 0.5, we have VO equal to VI plus VBEN. Okay, so this is what we have. Now, based on this, if you want to plot the relation between input and output, if it's VI, this is VO, what do you get? I mean, look at the middle. If it's 0.5, you got basically 0. If input is between 0.5 minus and plus 0.5, you got output is 0. And once more than 0.5, what do you get? You get this. This is going to be VI minus VBE, and at some point, it's going to saturate. We're going to look at the range, right? Because once it reaches like VCC, you have no more to go. Therefore, it flats out. And at the bottom, you got the same thing. It will drop and it will drop like this. And so the maximum voltage you get here is VCC minus VCEN saturate. And here is you get VCC minus VCC plus VCEP saturate. So here you see when your input is so big that your output or your transistor here will be like saturated. If this is saturated, your VCC minus saturation voltage is what you get for your maximum VO. If the bottom is saturated, you get the bottom. So that's why you have this range. And this is the plot over here, you got it. So in the sense that what if our input is here? If our input voltage, VI, is something like this. What do you think when you get for VO? Well, you see, if this is less than 0.5, what do you get? 0, right? So if you get, so we can draw a line, so 0. And then when it's more than 0.5, it's going to increase. But it's less than, and then when it's less than 5, you got 0. You got this. So which means when it's less than 0.5, it's 0. More than 0.5, you got VCC minus VPE. And then when it's again here, when it's less than larger than 0, minus 0.5, you got also 0. And then VI plus, when it's negative VI plus VCE, VPE, and you got this. So what you can see here is that the input is a pure sine waveform, but output, it got a little bit cut off at the zero crossing. It's have a period of time there's no output. What do you call this if you give a name? If you give a name, what would you name it? Huh? Diode? Yeah, close. It's a distortion. It's called a zero crossing distortion. What it means that when the input is close to 0, there's no output. And that's sometimes also called like hysteresis, yeah? Because it goes down and then there's like a little bit of region, there's no output, and then gets output and then get down. So this problem with class B is that it got distortion. But if you look at it, if we go back actually to the circuit, you probably already figure out this thing must have a high efficiency. Yeah, before even we derive it. Why? Because for positive half, the bottom is off. There's no current at the bottom. And all the current conducting from the top. And for the negative half, there's no current at the top, only current at the bottom. So which means this current is equal to this current. Therefore, efficiency must be high because the circuit only works half of the cycle. And the other half cycle doesn't work. So there's no loss. There's no loss every half cycle in the transistor, no current. So this is a much bigger improvement in terms of efficiency over class A. And we can derive the efficiency actually in a little bit. But before that, let's go with, this is they can see the output waveform. This is output waveform. And this is input waveform, this is output waveform. You can see there's a distortion at the near 0. There's a distortion. So therefore, this class B has this problem. This is sometimes called, this class is also called push-pull amplifier. Just to give you the name. Why is it called push-pull? Because when it's a positive half cycle, the current conducting, so it's a pushes current through the load. In the negative half cycle, the top is off, the bottom is on, the current is pulled from the load. So you push current to the load and you pull current from the load. So push and pull. So that you'll see the name. So push current through and pull the current out. So that's called a push-pull amplifier. But we can look at the power consumption. Let me actually derive possibly the current consumption. Then we can have a example. So for the power consumption, if we assume Vi equal to Vi and our output will be Vi minus VBE 1. Okay, so this is apparently, again, there's no voltage in the middle, there's a voltage at top of the one. We only write half of the equation. So this is for when Vi is larger than 0.5 volts. So to calculate efficiency, we're now going to make some assumption. So assume VBE1 or VBEN, they call it, or neglected. I mean, in real life, you can neglect it. But here, for the sake of calculating efficiency, let's do that. So in that case, you will have VO equal to 3I. What we do is we call it VO sin omega here. So if we do that, how much power is calculated in the load? Well, it's going to be this VO squared over 2 times divided by RL. So this is your output power PL. This is your output PL, right? So voltage squared divided by RMS, right? So power is equal to voltage squared divided by R, which is RMS. And RMS equal to square root of 2 maximum value or the peak. So that's how you get the losses, I mean the power of the load. So we have the power of the load. Now we need to calculate the power of source. Okay. So the power of the source, apparently, this is not the input. This is actually the power of the voltage supply. So if you look at the previous circuit over here, the power of this one, of the transistor, will be P equal to VCC times current IL, right? So the current flows through the transistor, so the total power supply, PS plus, is this much. VCC times L is the load current. And for the bottom one, you S minus equal to something VCC minus VCC times minus VI, so it's also VCC times I. So if we add this together, we got the power as, which is equal to each other, equal to VCC times I, which I equal to VO over RL, which is equal to VO maximum divided by RL, and then times the square root of 2. So that's what you get for I. Then we're plugging I over here. We can get our PS plus equal to PS minus equal to, yeah, so the average actually becomes, in fact, this is wrong. So it becomes 1 over pi VO prime, that's over RL, which is current, times VCC. Now, the reason is VCC is VCC is a DC. So when you use a DC, this is AC current, and you have DC. So when you look, DC times AC, when you get the average, which really equal to pi over 1. So that's how you get the pi over 1.
So this is our PS and P minus. So now we get our efficiency. We can now calculate our efficiency, which is going to be adequate to PL over PS plus PS minus, which we can plug in all these numbers. What we get is pi over 4, which is about 78.5%. So you can see here, instead of 25%, we increase efficiency to 78% maximum. Now we neglect VBE. So we have VBE, the loss will be a little bit, higher. I mean, the efficiency will be little. This is the ideal case. So we get efficiency, and we can have an example. So the example says PL equal to 20 watts and RL equal to 8 ohms. And VCC must be largely equal to 5 volts plus VO max. And we'll find what is VCC and also what is efficiency of the system. Now, since we know that PL equal to 1/2 VO squared over RL, so we have 1/2 VO divided by 8. So from here we can say VO equal to this 16, so it's PL divided by 16 and then square root. And PL is 20, 20 times, no, PL is 20. No, oh no, actually it's wrong. So this multiply. Sorry about that. So VO equal to 2 times 8 times PL square root, which equal to PL is 20, so it's like a 2 times 8 times 20 square root. That gives you roughly 17.9 volts. Very easily. So you know the output, so that's VO maximum, you get this much. And because VCC has to be larger than 5 plus VO max, so that will give you roughly 17.9 plus 5, we get 22.9. So we can select 23 volts. So we have 23 volts VCC. So that's what we get. And then we'll get to calculate efficiency. So we can now calculate IO equal to VO over R, which is, again, this is the peak value, which is going to be 17.9 divided by 8. So this is 2.24 amps. This is the current. And then we calculate now PL, because PL is given is 20 watts. That's given. So now we need to calculate PS plus and PS minus, which is equal to, we already have the equation here from last slide. So 1/pi times I0 times VCC. That gives you 1/pi times IO is 2.24 times 23. That gives you how much is it? 16.4 watt. So now our efficiency is PL over PS plus PS minus equal to 20 over 16.4 times 2. That gives you 61%. You see, this is the actual efficiency you will get at this piece of VCC and this output. So 78 point something is the maximum efficiency you will get. 61, you will never get more than that, but most of the time you will get something like here. The maximum power is 1/2. When the output is 1/2 VCC over pi, you will get 50% efficiency. Okay,
So this is maximum power output. So that's the maximum power. So sometimes when you design amplifier, sometimes you want maximum efficiency, sometimes you want maximum power. So when it's maximum power, you always get 50% efficiency. Remember from your circuit theory, when you want maximum power, your efficiency will be higher. When you want a maximum power, your efficiency is always 50%. Okay, so that's exactly true here too. But the efficiency will be higher at that time. So now we want to move on to talk about class AB. Well, why? Because now we have class A, we have class B. For class A, we got efficiency extremely low, 25%, which is not good. But the signal is perfect. So you got some advantage. Then for class B, we got efficiency extremely high. But the problem is that you got distortion. So how can we overcome the distortion, get a perfect waveform, but still maintain a high efficiency? This is where class AB comes in. So for class AB, we introduce a biasing voltage at the base. You can see the input is between half VBB. We have a biasing VBB. So what we can do, we can study this circuit. We start at VO is 0, see what happens. When VI is 0, and I can tell you VO is also 0. The reason is this. So if VI is 0, you got here is a ground. And if the VBB is larger than 0.5 volts, you know, and then this will be 0. Let's suppose this is 0.7. And what would you get here? You got 0. And if this is, and this is minus 0.7, and this 0, so both, you see, both are conducting. Both conducting. But how much current would you conduct? This both are conducting, but if output is 0, which means IL is 0, yeah, so IL is 0. So now all you have is a current called, let's call it IQ. So IQ will be equal to, you guys remember this equation for IQ? If you know VB, how do you calculate IQ? Yes, IS times e to the power of VBE over VT. So the current is determined how much VB is. So this VB cannot be too large, otherwise you will saturate. It can be too small, but otherwise it will not conduct. So it's about 0.5 volts, between 0.5 and 0.7. You can replace this simply with a MOSFET. It's very similar. It's almost the same, except that in MOSFET, you don't have current in the gate. But there you have a little bit of current at the base, that's all. Well, because BJT is easier to understand. Because you got fixed VBE usually, input. But for MOSFET, that voltage drop is not certain. So it's a little bit more difficult to analyze, yeah. So, yeah. So this is exactly, I mean, you guys, a good question, yeah. But people use MOSFET these days. But you know, in fact, even MOSFET is prevalent these days, but BJT is some of the like a 741 op-amp is so classical and it's so useful. They still make a ton of them for all kinds of applications. But when you go to like extremely high, like integrated circuit, very large scale integrated circuit, nobody uses BJTs. They always use like a, you know, MOSFETs. But again, BJTs are used, right? So, okay, so here we have this. So IQ apparently is what we call a biasing current. So it's a small, it has to be small, it shouldn't be big. Otherwise, you lose the idea of having a high efficiency, okay? So IQ is this, which is equal to IN equal to IP. N means the NMOS current, P means the PMOS current. So this is really ideal, right? So, and then what is VO then? Well, in fact, if VO should be VI, so we'll look at VI plus half VBB, and then minus VBE, and which is the output, or your VO can be equal to VI minus VBB over 2, and then plus VBE P. When this is when VI is larger than 0, this is when VI less than 0. You got, so because the input now is added, VBB over half is added to input. And basically, I mean, I cannot even reach. If you look at the base of Qn, the voltage is Vi plus half VBB. And then you minus VBE, you get output VO, right? So that's how you get this current. So, and then we have one. So this is one here. But when you have not, when your VI is not 0, when output is not 0, you have current. So current IL equal to VO over RL. And nowadays your current, so your current VI is this way, your IP this way. So you can see your IN is equal to IP plus IL. Okay, so that's your current. So when that voltage is no longer 0, and you have that. So but there's a little bit of caveat here, because when VO is not 0, the voltage across the base over there and across the base over like emitter over this one and then the top one is going to be no longer the same. They're going to be, because what happens if you see, if VO is not 0, there's IL. If there's IL, your IN is equal to IP plus IL, which means your IN is larger than IP because there's IL. If IL is positive, if IL is negative, which means your IN is less than IP. So these two currents are no longer the same. But based on the equation, based on this equation, based on this I equal to IS times E to the VBE over VT, and you can see if the I is not the same, which means VBE is not going to be the same, because IS is the same. So what we're going to do, we're going to write this down. So which means, but we here, if you use a loop here, I'm going to write this a little bit just for our reference. Oops, here. So I'm going to loop over here. This is called VBE, and this is called VBE P. So if you look at this two, what do you get for the loop equation? We would have 2 VBB plus half divided by half add together equal to VBB. So which means we have VBB equal to VBE n plus VBE P, right? So the voltage equation has to equal. So VBB on this side has to be equal to VBN plus VBEP. So those two voltages add together give you VBB. Now, again, now we bring back this, I n equal to IS times E to the power of VBE n divided by VT. And then we bring IP equal to IS times E to the power of VBE P over VT. So from here we can get VBE n Okay, now I can do this. I know you guys probably forgot a lot of math. What I can do is from here, I can do this. I can do IN over IS is over e to the power VBEN over VT. Then I take logarithm on both sides. So I get log IN over IS equal to VBEN over VT. Now I multiply VT on both sides. So I got VBEN equal to VT times log IN over IS. So similarly, I can get VBEP equal to VT times log IP over IS. So I can get this. Now I can plug in these two equations here to here. Okay. So when I plug in here, I get VBB equal to VBN, which is VT times log IN over IS plus VT log IE over IS. Now we can get the VT out, and the log plus, 2 log plus, what do you get? Put them together. You got log IN times IP over IS squared. Okay, I think I'm missing something. VT 2 times VT. Log IQ over, yeah. Okay, so I have, and then okay, so I get this equation here. Now I need to go back to the case where I is IL is 0. So when IL is 0, so IQ equal to VBB. Yeah, IQ 0, so it's half VBB. I mean, not half VBB. It's going to be equal to IS times e to the power VBB over 2, and then over VT. So I get this. So from here, I can get, because when when IL 0, you get IQ is a quotient current, which is equal to IN and IP. Remember from the previous equation here, we got IL equal to 0. So we have IQ equal to this. Actually, this VB is half. This VB is half VBB. So from here, we got half VBB. So therefore, we have IQ over IS. So I have IQ over IS equal to e to the power VBB over 2 times VT. And from here, we can get, I'm going to bring this one down here. So from here, I get here. So I get, VBB over 2 times VT equal to log IQ over IS. Yeah. So then I multiply 2t on this side. So I got VBB equal to 2 times VT log IQ over IS. So that's what I get VBB of this equation. So now I can plug in this equation VBB over here. I can write this one down to 2 times VT log IQ over IS equal to, that's 2 times, and then equal to, here is VT times log IN IP over IS squared. Okay, so now you see here, this VT is going to cancel. So I move VT on top.
So we get log IQ times IS, that 2 becomes squared because equals log IN ID over IS. So now this log is going to cancel and IS is going to cancel because this IS squared is cancelled. So I get actually IQ squared equal to IN times ID. So I got this, very simple. So that's the quotient current, which means I can simply get IN equal to IQ over ID, or I can have ID equal to IQ squared over IN. Regardless, it will be okay. Now, remember the previous equation we had is N equal to IP plus IL. And so now we can plug in this one equation over here to here, right? So we can get, we can eliminate one of those terms. So eventually what we get is, so we have IN equal to IO IQ squared divided by IN plus IL. So we got this one here. And then we multiply this one, we got N squared minus IN times IL minus IQ squared equal to 0. So this is the final equation we get. So if we know IL, we can solve for IL and IQ, we can solve for IN. Or if we know IN, IQ, we can solve for IL. So this is a very simple equation that we can find it. So this is where we want to do the actual example. Yeah, so we have time. So in example 12.4, so example, yeah. So okay, so before doing example, let me do one more thing is here. So if you look at this this thing, it's 2 emitter followers again to back to back. And if you look at the small signal, the voltage source becomes a short circuit. So this really, if you look at the output resistance, you will get, I mean, if you look at the equivalent circuit, so this one becomes here. That's the top one. And that's your input. And then the input is grounded. So, and then the bottom one, that's your input. So this is your output. You see, this is REP, this is REN, and your input is grounded. You remember when you do the equivalent circuit, input is grounded. Now, if your input is grounded, you should see this equivalent circuit. What do you have? Current source becomes an open circuit because VGS is 0 now. So therefore, the equivalent circuit becomes VO equal to one resistance and another resistance. So this resistance goes to ground, this should go in. So you got this one, RE1, RE2. So which means your output resistance equal to RE1 in parallel with REN, REP. So REN over REP. So that's your output resistance for the equivalent circuit. So apparently, if we know the REN, remember, you guys still remember how to calculate RE? Huh? Alpha by DGML, that's correct. And we can also use VT. So it's equal to VT over IN, and IEP equal to VT over IP. So we can plug in these numbers here. So we got R out equal to VT over IN in parallel with VT over IP, which equal to VT over IN plus IP. So VT is your summary voltage, and we IN IP with each of the actual current. Now remember this IN equal to IP plus IL, right? So and so therefore when your IN like increase, your IP would decrease, and typically this output resistance is going to fluctuate a little bit, but it's going to be very similar because when IN increase, IP will decrease. When IP decrease, IN increase. So that's what really make it a balance, right? So let me go through this example. So this example says VCC equal to 15 volts. IQ is 2 milliamps, and RL is equal to 100 ohms. And IS is given 10 to the minus 13 amps, which is some current. And what is VBB? Okay, if VO is between minus 10 to 10 volts range. So we want VO not exactly VCC, but it's between 10 and minus 10. So from here, remember for IQ, how do we calculate IQ? Is IQ is equal to IS times e to the power of VBB over half divided by VT. This is the equation. So from this equation, we can get VBB equal to, so VBB over half divided by VT equal to log, or to the, this is E. So log IQ over IS. So therefore we have VBB equal to 2 times VT times log IQ over IS. Now IQ and IS, they're both given. So 2 times VT is 25, which is typically given, and then log IQ is 2 milliamps, and IS is 10 to the minus 13 amps, right? So therefore we got this VBB equal to 1.1, really almost 1.2 volts. So we got this VBB has to be 1.2 volts. You can see it's not 0.5, but it's not, this number is typically between 0.5 and 0.7. So 0.5 is a transistor start to conduct. 0.7 is fully conducting. So between 0.5 and 0.7 is typically the voltage you need for the VBB. But times 2, so they got a 1.2. Okay, so for VO is going to be given, so we can calculate IL equal to VL over RL, because RL is given, and VO between minus 10 and 10, so we can calculate IL with a range, and then we can calculate using IN. Remember the equation we got from IN minus IL times IN minus IQ squared 0. This equation was derived from the previous slide. So now if you know RL, you know IQ, because IQ is given. For any given voltage VL, we can calculate IL because RL is given. So we plug in that RL into the circuit over here, we will be able to get IN. So we can get IN for any IL, for any IL. Then once you get IN, you can get your IP, which is IN minus IL. So you get this. Now you get IN IP, so which we get all of that. Yeah, so I think you can actually
like plot this diagram, and for each WL, you can get a certain I, P, and IN. You can get it, right? So that's really what you can get out of this, and then we can. Oh, so from here, if you get IN, you can get VBEN equal to this like IL, IN times e to the power of VBB over, no, sorry, that's wrong. You can get VBN equal to VT times log IN over IS. Yeah, over IS. So this IN times IS. So you can get this, and you can also get VBE P equal to VT times log IP over IS. Then you can get the really VBEP and VPN, you can get this number. Now remember, VPEP and VPN, when you add them together, you always get VBB. Okay, that's as simple as that. So I'm not going to get actual numbers, but this is, I'm going to actually have to, I can stop here. But really, if you have the summarize class A, class B, and class AB, and class A, the advantage you have is a sinusoidal wave. The disadvantage is low efficiency, 25%. And for class B, it's high efficiency. You got efficiency maximum 78%. But there's distortion of wave. It's zero crossing distortion where you get this distortion. And when you get a class AB, you got no distortion. You got high efficiency. We didn't actually derive efficiency, but the efficiency is actually pretty high. The reason is we have just a little bit of biasing current. You know, the biasing current example is 2 milliamps. But for this type of circuit, the actual load current is going to be hundreds of milliamps or maybe amps. So that's why the efficiency is similar to the class A, similar to class B. Okay, the book has derived the efficiency. Yeah. Why is it high efficiency? Or the disadvantage? Oh no, this is not disadvantage. You're right. No, this is not disadvantage. So this disadvantage is added power supply. So the advantage is high efficiency. There are two advantages, okay? Sorry, yeah, good catch. But added power supply, you can actually do what we call a biasing. It's not actually a power supply. It's going to be another circuit to bias the gate or the base. So that is something we will not be covering in this class. It's too much, okay? And class C amplifier, well, we're going to skip it as well. So we don't have time. But you guys get an idea, right? So class A, you got some advantage. So in the future, if you go design something, your boss asks you get a job, you must go design this amplifier. And you analyze, okay, well, the losses, the whole power output is only 1 watt. Let's go with class A. Simple, no distortion, great. But if you go with high power, if you don't care about the distortion, like you can go with class B. It's simple and it got high efficiency. But if you want a good signal integrity, no distortion, you also want high efficiency, you have to go to class AB, which will give you high efficiency, no distortion, but more complexity, right? But anything that you gain, you're going to lose something. Of course, there's nothing for free, right? And the class C also has some applications. You can read it. And of course, if nothing works, go to class D. go to class 584. You will know how to design a class D amplifier, which means when we go to like electrical machines, when we go to kilowatts, when we go to tens of kilowatts, even that 78% efficiency is no good. You're going to waste a lot of power. So we do class D. We can go to efficiency as high as 99%. But it's more complexity, more cost. Yeah, go ahead. No, it's oh, I swapped. Yeah. Yeah. Let me correct it before. Yeah, you're right. You're right. Good. Yeah, I made it in flip words. So the advantage is high efficiency. And the disadvantage is distortion. Okay. So thank you. That's a good catch. Yeah. So again, so this is the end of the lecture today. Okay. And unless you guys have any questions. Okay, if not, we're gonna see you next week online. And we're gonna be talking about some fun stuff about op-amps. A lot of equations. But it's gonna be interesting. Yeah. So your project will be graded this week, and you have your quiz. You can pick it up if you want it. If you don't want it, I'll throw it in the garbage. I'll shred it. But yeah. Monday and Wednesday, I'll be online next week. Yeah. No,
Next week.
only online, right? Next week is only online. Yeah. Huh? Homework? No. Homework we cannot push back anymore because there's no time really. Because you guys exam on the 3rd, so we can't do anything after that. But I already posted all the homework, so you should have access to it.
Question, will we take our plan on?
Yeah.
Will it be open book, open note?
Open book, open notes. If you want to take it as a testing sentence,
Yeah.
schedule it with them, okay?
Okay, all right,
Yeah.
I just wanna.
Yeah.